Thank you. All right. Hi, everyone. I'm Sydney. I'm the volcanologist at Laminar Research, where I work on, Explain. I'm assuming that neither Explain nor Laminar Research are big household names, so let me introduce both real quick. Laminar Research is a small, privately owned company founded in 1995. And for reference, this was me in 1995, 30 years ago. I wasn't working on Explain then. I know, crazy. For the first 9 years, the company was a one-man show, and it has slowly grown since then. This is basically the whole team right now, and there's really only two noteworthy things about Laminar Research. We're fully remote, spread across the whole globe, and since 1995, we've been exclusively working on Explain, so we are a one-trick pony. Explain is a FAA-approved professional flight simulator. That's fancy talk for it can be used for real-life pilot training, and it is in use by flight schools around the world. And but our customers are also just regular aviation enthusiasts and generally come from all walks of life. Just to quickly clarify, though, we are not Level D certified, so we can't be used in these really cool full-motion simulators, and we're just kind of lame. And we never had a clean break or fresh start or anything, so we are essentially working on the engine of Theseus. All right, was able to say that word. And the current code has a direct lineage to these old versions all the way back to version 1. And we are currently shipping and maintaining Explain 12, which came out in 2022, and before it, Explain 11 came out in 2017. And our release cycles tend to be quite long, and we aim to release 1 or 2 major feature updates per year, plus the couple of patch releases. And we support all major desktop versions, platforms. So Windows, Linux, and macOS. And technically, there's also a separate mobile version, but for the sake of time, I'll just ignore that. So today, I want to just give you a quick glimpse into our tech and what we do. Given its age, there is a lot of history that could be talked about, but I'll let Grandpa talk about the trenches, and I'll just focus on the more recent stuff, so the past 8 years. I want to tell you about a really bad decision that we made decades ago, and that is now haunting us. How we modernized our rendering engine from its OpenGL roots to Vulkan and Metal in order to take better advantage of modern hardware. And then just a quick look at what we're doing right now. So we develop most of our tech in-house, and we have a custom engine called X-System. Although the word engine might give the impression of a clean stack like this. Nice rendering API, clean separation between application and client code, and let me just tell you that is absolutely not the case. This is what we're doing. Since we only work on Explain, it's just one large monolithic code base. I think the term is organic, and we have varying degrees of technical debt, and for the longest time, there wasn't even any rendering API or anything. It was just application code, which is called OpenGL directly. And of course, we had some high-level objects that I guess you would consider engine code, but yeah. But even worse, we were actually still using OpenGL 2.1, and for those who don't remember the dark days, capability-wise, that was kind of between DirectX 9 and 10, although much closer to DirectX 9. And it goes without saying, but not having compute shaders and just using vertex and fragment shaders was not a good way to have a modern title. There was essentially no ASDO, and depending on the system and hardware, we had up to 50% of our frame time in the drivers. And we also had the usual stutters from runtime pipeline discovery and and all of that, since we have a lot of streaming content. So by 2017, around the release of Explain 11, we really wanted to move away from OpenGL and adopt Vulkan and Metal. to stay competitive and solve all of our headaches. And that meant we had to actually build a rendering API for ourselves, which we creatively named GIFX. And we also had to get all of the raw OpenGL usage out of the application code. And this is roughly what we wanted to end up with. And we had a couple of other goals that we wanted to achieve. We wanted to have no more mid-frame PSO compilation. And we didn't want to oversubscribe VRAM. So essentially, we wanted to remove 2 large sources of stutters from the sim. And we wanted to ship spec-conform code to give Explain the best chance to run on hardware in the future, because Explain 9 from 2008 is still in use by some flight schools. So we don't support it anymore, but it still has some use. And we also didn't want to break any plugins, and that might seem a bit odd as a goal for a rendering API, but it'll make sense in a second. There is Horus. And lastly, we wanted to ship this as an update for Explain 11, not as a new major version, which meant we actually also had to write a bug-for-bug compatible OpenGL backend. And starting with the OpenGL backend actually was quite beneficial for us, because it allowed us to keep shipping Explain and slowly write new APIs and move code over from the application side into our backends. And that also meant we didn't want to add any graphical improvements. We just wanted to get the same frames again, just a little bit faster, less stuttery. So to explain the plugin compatibility bit, I have to very quickly introduce the SDK now. It's probably best to think of Explain as a very open platform, which users can completely customize. Our SDK is freely available and lets users build new aircraft, customize, and build entirely new scenery, and generally change just about anything. We have documentations for the majority of our file formats, including some that aren't part of the public API. And long story short, heavily customizable. People love doing that. And remaining compatible with the large add-on ecosystem that we have is hugely important for us. We essentially live in symbiosis with our third parties and their add-ons. The SDK was first introduced with Explain 6 in 2001, and just again, this was me at the time. I want you to know that I am absolutely innocent. The SDK comes from a time of 30-bit address spaces with limited memory, largely single-core CPUs that were really slow, and as such, plugins are just shared libraries that get loaded directly into our address space with no isolation or sandboxing mechanism, and that has definitely never been a problem for us once. As a side effect of this, the SDK is heavily callback-based, and everything was built around getting data from plugins just in time. We didn't have any memory back then, and for example, the animation system to update a bone matrix will do individual plugin callbacks to get each single value. Great thing. In a modern engine where we would rather have nice structures of arrays, that is an absolutely fantastic way to destroy all caches. But plugins also want to draw stuff, whether for avionic instruments or just general UI. All of this is plugin drawing here. And I now have to admit that the SDK doesn't actually have a drawing API for plugins. Instead, it just expects plugins to use the OpenGL context from Explain to do all of its drawing. Depending on how high you are, this is actually kind of genius, I guess. It gives third parties a lot of flexibility to draw whatever they want, and it also made this part of the SDK really easy to implement for us. But in reality, the drawing needs of plugins are relatively limited, and our third parties are generally aviation enthusiasts and not graphics programmers. So even OpenGL is way too low level for them. Because of this, plugins generally just use the legacy fixed function pipeline and immediate mode APIs. Shaders are complicated after all. And on macOS, OpenGL comes in 2 flavors. You can have a OpenGL 4.1 core profile context without fixed function pipeline support, or you can get an OpenGL 2.1 context that obviously does. And this is how we ended up with an OpenGL 2.1 engine in 2017 that's tied to plugins. So while we modernized our engine to use Vulkan and Metal for internal use, we also had to make sure that we didn't break any single plugin out there. And the solution that we came up for this is the plugin bridge. We figured if plugins need OpenGL, we could just give them OpenGL to do all of their drawing with, and then just magically share the results with Explain. Internally, this is implemented with OpenGL interop provided by both Vulkan and Metal, and Explain takes care of all of the necessary synchronization and resource setup. And this allows plugins to just work without any changes since they're still seeing their OpenGL context as normal. Under Vulkan, OpenGL interop is at least theoretically quite straightforward, although in true Kronos fashion, it's implemented using a zoo of extensions for both Vulkan and OpenGL, which allows exporting of Vulkan device memory allocations as either handles or file descriptors, depending on the platform, which can then be imported into OpenGL. Since those extensions work with memory directly, there's a lot of flexibility here, but we use it exclusively to just share some render targets. We bind an OpenGL texture and a Vulkan image to the same shared memory region, and then both APIs are able to see each other's side effects on that memory. And in addition to memory sharing, these extensions also provide shared semaphores, which are used to synchronize both Vulkan and OpenGL with each other. There's a diagram. Oh, it's actually readable. There's a diagram here of how this works. Don't do this, by the way. It's pretty straightforward. When you go from one API to the other, the source side signals a shared semaphore, and then there's a queue submission, and then the destination side waits for the semaphore and before executing any of its commands. On Metal, this looks very similar in theory, except that just like OpenGL, Metal is deathly afraid of admitting that memory is real. So the workaround is to use an I/O surface, which is as a shared memory resource, and that is a kernel backed pixel buffer that can be passed around as a mark object. We then create a Metal and OpenGL texture from that I/O surface. Well, I went too far. We then create a Metal and OpenGL texture from that I/O surface to be able to use it in the respective APIs, and there's a lot of restrictions on I/O surface backed textures. They are linear tiling only, so they're super slow to access. They don't support mipmaps, which is really awkward if you want to map them into 3D space for, I don't know, avionics. And under OpenGL, the created textures are also texture rectangles only, so you have to access them with absolute coordinates instead of normalized ones. Sane people would have used this as a wake-up call, but Laminar Research doesn't hire sane people, so we went on and work around all of these by creating additional shadow textures and then liberally blitting them when we go between Metal and OpenGL. Both bridge implementations require command buffer submissions for every single time you want to switch from one API to the other. That isn't great and not avoidable, so there you have it. And because both bridges require slightly different implementations and handling of the shared resources, we wanted to hide all of the implementation details in the backend implementations. It's kind of readable. Application code can just create a texture with a shared flag and have it magically show up in OpenGL. And under the hood, backend texture implementations just take care of all of the shared resource setup and creation of any of the shadow textures. And then our command buffer class has APIs to transition to and from the OpenGL bridge, even in the middle of an active render pass. Again, don't do any of this. Which will submit the underlying real command buffer, and when returning from OpenGL, start a new command buffer, and also restart any interrupted render passes. That makes mixing of plugin and Explain rendering really, really simple. And despite being a major milestone for us, the bridge makes for really bad screenshots. Here's one anyways. The avionic displays here are drawn by OpenGL, and everything else is drawn by Explain in Vulkan, which is really cool and insane. And for the non-aviation nerds, the artificial horizons, those thingies here, they show the aircraft's current attitude, and blue is the sky, and dark orange is the ground. And usually when it looks like this. Something really expensive is about to happen. But luckily for Lloyd's of London, I think it's pretty clear that this plane is actually not upside down. OpenGL and Vulkan/Metal see the same underlying resource, but have their own view of it, so it's really easy to get the color formats incorrectly. Really easy to fix, though. Here's what it's supposed to look like. And of course, technically, this was the last thing we actually worked on for the port, since we first had to write the Vulkan and Metal backends. But it's probably the most unique aspect of X-Plane, and I thought I'd start with that. Also, thanks for the person who kept coughing on me on the plane right here. I love having a plug nose. So shaders were the first thing that we actually worked on for GIFX. As with every good OpenGL engine, our shaders used to ship as plain text files on disk and were authored for GLSL 120. Yeah, I get that reaction a lot. For GIFX, our shader targets became SpearV for Vulkan, MSL 2.1 for Metal, and for OpenGL, we still needed to produce GLSL 120 shaders. We did some experiments with SpearV Cross to see whether it could produce all of our targets, especially the legacy GLSL1, and it turns out that it, for the most part, could. Although it did emit some incorrect built-in usage and also generated real spec constants that were obviously not usable for us. All of that's fixable with regex. And out of that early experiment, we built our offline shader compiler, creatively named GIFXCC. The first C stands for shader, which uses GL slang to build and optimize the initial SpearV, and then uses SpearV Cross to transpile it to our other targets. And we also use SpearV Reflect to generate additional introspection data for using the shaders at runtime. The shaders are now written in GLSL 460, and on the right here you can see a snippet of one of our shaders, and if you know GLSL, you will note that the interface declaration is weird. I got the impression nobody uses GLSL, so this might just look normal to you. It's not. We didn't want to put the burden of descriptor set and bind point assignment onto the shader author, especially since we came from a world of OpenGL with its quasi-magic resource bindings. So bind point allocation is done by GIFXCC in a pre-processing step that also generates common descriptor set layouts for our Uber shaders, and it's also responsible for resolving and assigning metal bind points, since those aren't not compatible with Vulkan's two-dimensional descriptor set scheme. Driving all of this is a JSON description of the shader with all of its possible specializations, and from this the compiler will compile all shader variants to SpearV and then transpile them and all of that. We also generate C++ introspection data to automate resource bindings in the code as well. This includes correctly aligned C++ structs for constant and storage buffers, as well as descriptor set glue code and shader specialization information. You probably guessed it already, but we don't use a fancy shader-based node setup or anything. It's all done manually, and our client code is responsible for gluing all of the right resources to the shader. Our frame is done pretty much programmatically and not data-driven, so makes sense. We also generate machine-readable introspection data, which is used to actually facilitate the resource bindings at runtime. This way, the programmer just has to fill in a bunch of C++ structs, and GIFX will automatically fill the descriptor sets and bind the resources. Here's the same shader again, but on the C++ side. First, we look up the shader and layout, and then build and stream a descriptor set for it. And machine-readable introspection data is responsible for extracting the data from the struct into a real descriptor set and a metal arc buffer. And it also validates that the programmer has provided the right resources and of the right shape and size. So we end up with almost no boilerplate on our shaders, which is pretty cool. Shaders, of course, also mean pipelines. And I mentioned that one of our wish list items was to not have any runtime PSO compilation, which a lot of games achieve by preceding a PSO cache in some way. But because we have very unpredictable content that is constantly streaming in at runtime, that wasn't really an option for us. Likewise, just building every possible PSO isn't an option either, because we have tens of thousands of shaders in our Uber shaders, although we actually do that for our smaller shaders with just a couple of variants. But for the main material shader, we have a material cache, and material usage is tagged with the required capabilities upon their creation. And this is then used together with the current settings to figure out what pipelines need to be built for which render targets. And none of that is done automatically either. We have a horrible, hard-coded truth table that does all of this. WTF indeed. For obvious reasons, this breaks super easily, and it is super easy to build either way too many or too few pipelines, and it has probably been the most painful and consistent source of bugs for us, and I can't wait to replace this one day with a more data-driven solution. For memory, we use the excellent Vulkan memory allocator library. Because one of our goals was to never oversubscribe VRAM, we use the memory budget extensions to monitor the heap usage at runtime, and then potentially page textures into a lower resolution if necessary. Users can and love to load Xplain up with add-ons, most of which want to advertise 8K textures for marketing reasons, even though some of them are completely wide. Thanks for wasting the VRAM. And we also support projecting satellite imagery onto the scenery, which increases the overall quality of the mesh, but tends to have a lot of very large textures with usually around like 1 centimeter per pixel resolution or better. And we continuously reevaluate the resolution of those based on how much size they take up on screen. And all of this means that there's quite a lot of memory traffic as textures get paged in and out, and scenery gets loaded in and unloaded. And naturally, this leads to a fair bit of fragmentation, which is partially curbed by sorting allocations into different VMA pools depending on their predicted lifetime. And we also actually defragment our VRAM at runtime in the background. The defragmenter builds up a list of resources to be moved, and then every single frame, it moves a couple of allocations on the graphics queue to avoid causing too many bubbles and frame spikes. Goes without saying, but the defragmenter is quite fragile and has a lot of resource tracking overhead, so ideally we would love to get rid of it. And at some point we thought, oh, we could just use sparse for everything and just have page-sized blocks and bind all of that. Every modern GPU has an MMU, and we already deal with virtual memory, so should be easy. No, sparse bindings are incredibly slow on every single driver stack, especially if you start using page-sized blocks for everything and have a ton of individual regions to bind. I know some of the IHVs are here, and if Kronos is listening, please give me a nice sparse binding API that does this quicker. Thank you very much. So I know so far this talk feels like a how to not write an engine talk. In general, our engine these days is quite normal, if such a thing even exists. But I figured at this point everybody has done a we have adopted modern APIs talk, and I just figured I'll do like a couple of things that are unique to us and maybe interesting. We get away with most of this because we're a small team and we work on a single title. None of this really scales beyond that, but speaking of the team, though, during our modernization effort, the graphics team grew from just 2 to 3 people. And in total, it took us about 2 years to get the Vulkan and Metal backends shipped to our users, most of which was just refactoring the application code and getting the raw OpenGL usage out. Once we had ironed out the most egregious bugs over a grueling 9-month beta period, our users were quite happy with the improved performance, but the biggest complaint we got was that our customers would really prefer better graphics and not just the same frames, just faster, which reminds me, this is Xplain 11. And I feared coming to a graphics conference with a screenshot like this would empty out the room, but I think you're all committed now or sleeping, so let's talk about Xplain 12. We almost immediately dropped the OpenGL backend when we started Xplain 12 and went full in on the modern APIs. Having cleaned up the rendering backend code and having created a modern rendering API, we really wanted to tackle the graphics next and take advantage of our new toys and capabilities and just play much nicer with modern hardware. So yeah, this is what we've done. One of our biggest goals was to exclusively use physical units in our rendering engine, which isn't just useful for the implementation side, but also for the artists and third-party developers. The aviation industry is highly regulated and spec-heavy. Kronos could use some pointers from them. And everything is regulated, every single light, nothing is up for chance. So being able to plug those values in directly is super nice for us. And we also replaced the uncharted tone mapper with AGX and implemented a photometric rendering pipeline, and has drastically improved the overall look and feel. This is the same scene again, but in X-Plane 12, and I think we did slightly better. Unfortunately, one of the biggest complaints we got after shipping is that our cockpits are too dark now. You can see that in the top here. I have to say, technically, this is realistic, all right? Cockpits are really dark. They're small enclosed spaces with tiny windows, and that makes for dark rooms, but our eyes are really good at dealing with that sort of high dynamic range. So we added exposure fusion in an update to improve the virtual pilot's eyesight. And yeah, you can see that at the bottom here. Of course, if you're one of these people with too much money and you happen to have an aircraft cockpit at home and just need X-Plane to drive the visuals on the outside, that was never a problem for you. But maybe your bank has problems. We also wanted to improve the clouds and atmospheric rendering. You kind of saw it earlier already, but this is what our clouds look like. The clouds were simple stacked billboards, which had a ton of overdraw and also didn't allow us to have smooth weather updates over time. So while they were both ugly and unrealistic, at least they were slow. Cloud plugins remedy some of this and were incredibly popular back in the day, but we figured with X-Plane 12 we would just make that kind of plugin obsolete and move to volumetric Raymarch clouds. So let's start with the atmosphere, not with the clouds. This is the golden hour in X-Plane 12. Our atmospheric rendering is heavily based on Hilliard's work on sky and atmospheric rendering with some small tweaks. Instead of sampling the sky coefficients for just 3 wavelengths, we integrate them across the whole visible spectrum. This improves the look around the sunrise and sunset hours, since it let us better model the spectrum in which ozone absorbs light. And on the top here, you can also see, can you? Oh yeah. Cloud shadows casting into the sky, which is just, for X-Plane 12, we were joined by our 4th graphics programmer, and he is really into atmospheric and cloud rendering, and he's been going ham. And at the bottom, you can see the blue hour being properly blue, which is probably our biggest improvement over the original paper from Hilliard. And here are the new volumetric clouds again, and they are much better than the billboards clouds, especially at depicting large range of conditions like those towering clouds. For the direct light component, we use Beer's law to keep everything nice and physically correct, and for the indirect light, we use a combination of the modification of Beer's law as proposed by the Horizon Zero Dawn paper on volumetric cloudscapes, together with the multiple octaves approach from Venninger's paper on art-directable multiple scattering. This gives a nicer and more physically accurate approximation to multiple scattering that still includes Beer's law, which results in these really nice powdered sugar effect on the clouds. And we can now also update our clouds over time dynamically, and that's really useful for longer flights. We also wanted to improve our depiction of vegetation. I don't know why, it looks great. Previous versions used quad billboard meshes for their vegetation and crammed large number of object variants into a relatively small atlas texture, which certainly didn't help the up-close look. To limit the amount of geometry extruded, the vegetation density was also quite sparse, even at high rendering settings. And the scene here is supposed to depict a super dense old-growth forest. Yeah. We definitely could have improved the billboards with better art, but for X-Plane 12, we wanted to have actual 3D trees with more variations and more density. So instead of extruding geometry, we now have create a persistent point cloud for vegetation segments and create a large buffer with all the meshes. Since we wanted to have a lot of density, each point in the point cloud is only 24 bytes and quite tightly packed. The rotation component, for example, is encoded as 2 half floats into a single UN32. At runtime, we then cull those in an initial coarse culling step on the CPU, and roughly culling every segment, and then everything else happens on the GPU. The first step is a compute shader that culls the individual points using subgroup ballots to create a new list of compacted points. Instead of duplicating the data, we only write a reference to the original point and some individual pre-computed animation parameters, resulting in just 12 bytes per point. And then in a second step, we build a large number of instanced indirect draw parameters, one for each culled point list. And then finally, in the vertex shader, we use custom vertex fetch to read from the mesh buffer and use the culled point list to place all of the vegetation objects. The vertex shader is also responsible for creating the procedural wind animation, which is based on a super old GPU gems article from Crytek. Thank you. And as you can imagine, there is a lot of indirection in the system, but it allows us to put hundreds of thousands of objects into the virtual world with minimal VRAM cost. And one of our goals was high density, since we have very large levels and view distances up to around 100 kilometers, and we wanted to have vegetation up to the horizon. So here is that old growth forest again, this time in X-Plane 12, and being able to efficiently place trees. It just looks green now. It's a lot of trees. And here's the same location again, but like slightly zoomed out on the left. And on the right, you can see that we also use this system to place smaller ground clutter objects like broken branches, stumps, and rocks. There's one hiding right there. To have manageable performance, the 3D trees have quite aggressive LODs, with the last step still being quad billboards, using the old school low-resolution Atlas texture to draw them efficiently, but of course, now that they're at a distance, that's a lot harder to tell. But when looked at from steep angles, the billboards really, really show. You can see that in the top here. Although you would think that might be a common view for flight sims, but like a more shallow angle like this is a lot more common unless, again, something expensive is about to happen. We did experiment with octahedral imposters to improve the look and also give the billboard trees a lot more volume. Our initial testing was super promising. You can see here our Minecraft test tree that is rendered as an octahedral imposter with proper self-shadowing, and it looks great. Unfortunately, by the time we got around to implementing this, our artist had already made 2,146 vegetation objects, and baking all of the Atlas textures for those would not have worked. I think we can maybe make this work with more sparse binding. So hit me up about that new API. Thank you. And we finally also added seasons to X-Plane. Previous versions were always set in summer, so we figured a good way to stop the artists from making even more vegetation objects would be to get them to make seasonal art assets. Besides just more art, the scenery data now also encodes information about when the seasons change throughout the year, and based on that, the loader picks which seasonal assets to load. And for things with gradual season changes like vegetation, we also support loading an additional set of textures and then interpolate between them at runtime. So technically, our seasons are actually still static and resolved at load time, but I'm pretty sure X-Plane crashes before you wait there for like months to find out. One thing to note is that the snow in the winter screenshot is not coming from the art. It's a post-processing effect that is applied directly to the G buffer. On the right, you can see what the winter scene looks like without any snow applied. So I'm happy to report, unlike the real world, we are ready for climate change. In addition to snow, we also have weather effects for surface wetness, standing water, also known as puddles, and ice. And you can see the rain and puddle effects here, and they all use the same post-processing effect. When rendering our normal G-buffer targets, we also render a weather mask, which encodes how much each pixel gets affected by rain, water, ice, and snow. And then after rendering our G-buffer, we modify it in place using a compute shader that uses the weather mask and the actual weather conditions. And then the shader modifies the albedo normal and material change based on how strongly to modify each pixel, which is essentially the dot product of the weather mask and the conditions. Rain will tint I went a little too fast. Rain will tint the albedo darker to make it look wet, and puddles will make the material glossier and also smoothens out the normal if they aren't already, and snow and ice work similarly, but they tint the albedo white. And afterwards, we just resolve our gbuffer as normal to get our HDR target. So here, the relevant part, a little bigger again. On the left is the final scene. Top right is just the weather mask. The green channel encodes how much puddles to apply, and you can see like it puts them where they are in the weather mask. And the blue channel encodes where to put snow, or like how the surface accumulates snow, but because there is no snow in the current conditions, none is applied. And on the bottom is what the scene would look like if we just resolve the gbuffer without modifying it. So staying with the water, turns out our level designer was quite lazy and just covered 70% of the level in water. So, yeah, I know. So this is X-Plane 11's water, which was just a flat mesh, and it looked okay from a distance, but up close it tended to look a lot more like an oil spill. It also always came in this nice blue color and was completely opaque. This is supposed to be the Rio de la Plata, which in real life is extremely muddy and dirty and not this blue. So for X-Plane 12, we wanted to also have art-driven turbidity and tinting of the water, as well as 3D waves and boat wakes. And on the right, you can already see our new water. Since our base mesh did not have enough resolution to properly depict 3D waves, even with tessellation, and we didn't want to spend the additional memory budget on more geometry, we instead used the projected grid technique for views close to the camera and fall back to the low-resolution base mesh in the distance. There's one big gotcha for us. The world is genuinely round in X-Plane. Sorry, flat earthers. So projecting a flat mesh doesn't actually work for us. Instead, we use an off-screen pass, and we render the low-resolution base water mesh from the scenery, including water tint, color, and normals. And then we also draw boat wakes as quasi-particles on top of that. And in a compute shader, we then project a uniform grid in screen space against the depth buffer and reject any grid points that aren't hitting any water. And then we build an index buffer that stitches the surviving grid points into a high-res water mesh. Shaping the waves, of course, done with FFTs like everybody else. And then we use those to translate the grid points vertically, and we also move them horizontally to achieve tighter wave crests. And because the wakes are included in the off-screen pass, it also automatically ends up displacing the mesh as well. So here's how everything is composited. We start without any water, and the ocean floor is drawn as a black void. We then draw the generated 3D water mesh on top to fill in the near view, and it might be hard. Yeah, you can't see, but there is a wireframe mesh, and in theory, you could see that it's a nice uniform grid. Here's the wireframe view again, but a little bit more zoomed out, and you can see how the projected water grid ends up providing a ton of resolution up close to the camera. And you can also see a couple of tracks where the water meets the land, and we ended up discarding grid points. We then fill in the rejected areas together with the far water by just drawing the base water mesh and letting the shading sell the illusion of waves in the distance. And the water shading is based on Bruneton's mesh to BDRF water rendering approach. And you can, I left the wireframe on, and you can kind of see the transition to the far water, like in the distance where it starts looking different. So here's a couple more shots. On the left is the Rio de la Plata again, this time nice and muddy and dirty. And then on the top, you can see the aircraft carrier project US naval power and wakes. And on the bottom is the same location again, but with overcast conditions, and the water turns like a nice steel gray. And now I have to make a bit of a confession. I tried to sell you the plugin bridge as like this great thing that you all should implement. But I was partially lying. I mean, it works great on some drivers, and it is a real solution to our problem. but not on all drivers. In particular, the AMD driver on Windows. The AMD driver on Windows has a lot of CPU overhead each time we transition from OpenGL back into Vulkan. And for Explain 11, we just told users, well, just use the OpenGL backend and stop bothering us. But since we've removed the OpenGL backend, that was no longer an option for us. Luckily, someone has developed a Mesa OpenGL driver that emits Vulkan. And we speak Vulkan, and that thing does the fixed function pipeline insanity. So we just integrated Zinc, which was that's, by the way, the name of that driver, which was surprisingly straightforward. We contributed a couple of missing extensions that we required, and we also modified it a little bit to use our Vulkan device and forward its memory allocation requests to us. So there is no actual transition between anything between us and the driver anymore. And this gives us a custom OpenGL 32 DLL or libgl.so that we just load early on, and then plugins are none the wiser. And this solves our performance issues and shaves off about 10 milliseconds of wall time every single time we do an OpenGL transition. And the other really cool thing is that we now get to step into the OpenGL driver because everybody wanted to do that. There are, of course, a few gotchas. Not everything supported by OpenGL is correctly emulated, especially some of the esoteric line drawing features that nobody should be using. Right? Like, who uses stippled lines? Our third parties. But let's ignore that and just go on. We now ship a real OpenGL driver with Explain in an effort to double down on our bad decisions. And that brings us to today. Explain is 30 years old, and we still have a lot of things planned. A big source of pain is our scenery engine, which dates back to Explain 10 from 2012. It's been modified over the years to include, things like season support, but at its core, it's based on vector data, which scales really well until it doesn't. So our next generation scenery system is being built around raster data instead, and together with that, we are also streamlining our coordinate system to use a local tangent plane one. Coordinate systems in flight simulators are super fun, by the way. Another vestige is our model format, which dates back to Explain 8 from 2004. We are working on bringing GLTF support into the engine as an alternative, and those are some long-term projects. In the short term, we have performance as an issue. The shipping Explain is still largely single-threaded, but having developed GIFX from the ground up to be multi-threading capable and having modernized large parts of our application code these days, we are really, really close to shipping an actually multi-threaded renderer, and it's based on the ideas from the Destiny multi-core engine taught from GDC, whatever. And I don't remember dates. And then there are a few smaller things that our users would really love to have: TAA, DLSS, FSR, and all those nice things. But the engine doesn't produce motion vectors at the moment, so we're working on that. And maybe one day we'll even build plugins a nice drawing API. Who knows? Maybe we'll ship another driver. And that about sums it up. Of course, it's not just me working on Explain, so I want to give a big shout out to everyone at Lamina Research, especially my partners in crime on the graphics and engine team, and also the art team that makes anything we do look good. And of course, Austin Meyer, the creator of Explain and our benevolent dictator for life. And I don't know how I'm doing for time, but there might be time for questions.